This paper is about fast and provably good seedings for k-means. K-means is a non-convex optimization problem, and most solvers such as Lloyd's algorithm are only guaranteed to converge to a local minimum. For example, consider this dataset. Depending on the initial cluster centers, one may end up with two different clusterings. If we start with a good set, we obtain the global minimum on the left. If we start with an inferior set, we are left with the extremely bad but still locally optimal solution on the right. This is why seeding, the task of finding initial cluster centers, is critical in obtaining high-quality solutions for k-means. In practice, there are two common approaches for seeding. In a naive approach, one samples data points uniformly at random and uses them as the initial cluster centers. This is extremely fast, but the resulting solutions can be arbitrarily bad. The second option, the state-of-the-art algorithm k-means++, provides substantially better solutions using an adaptive sampling scheme. However, the algorithm requires k inherently sequential passes through the full dataset, making it impractical for a massive data setting. In this paper, we propose an algorithm called assumption-free KMC² that is both fast and produces high-quality seedings. We efficiently approximate k-means++ using a Markov chain where data points are states. First, a data point is randomly sampled as the initial state. Then, a further data point is sampled to act as the candidate for the next state. A randomized decision then determines whether the Markov chain transitions to the candidate or whether it remains in the old state. This is repeated many times, and the last state is returned as an initial cluster center. By design, the stationary distribution of the Markov chain is a true k-means++ distribution. Informally, this implies that we can approximate k-means++ well if we simulate enough steps. Our analysis shows that the Markov chain mixes fast and that a small number of steps are sufficient, ensuring a low computational complexity. Based on this idea, we propose a seeding algorithm for k-means that can be used as a drop-in replacement for k-means++. It is easy to implement and code is available online. We theoretically analyze the expected solution quality of the generated seedings and show that they are provably good without any assumptions on the data. Our experiments show that the proposed algorithm efficiently approximates k-means++ and outperforms prior work. Compared to k-means++, we have observed speedups of up to 1,000 times at a relative error of slightly more than 1%. If this sounds interesting, please visit both our oral presentation and our poster at NIPS 2016. The presentation is on Tuesday at noon, while the poster is on the same day from 6 to 9:30 in the evening. The poster number is 175, and an extended version of the paper plus an implementation of the algorithm are available online.